Okay, good morning everyone. Welcome to the first lecture from me in the second series of lectures. I know we have more than 5 lecture slots, but these lectures last more than 1 hour, so I'm going to stop them and, if I get reminded to, and carry on. So the menu looks something like this. So yesterday I hope you learned a lot about the hydrogen atoms. Today I'm going to talk about general why we do astronomical spectroscopy and atomic spectra. Then we'll move on to molecules, going through molecular motions and rotations, vibrational spectra, electronic spectra. And then my last lecture, you get an exam at the end of this course, which will be a multiple choice exam. My last lecture is not part of the exam. It's actually spectroscopy of exoplanets, how you do it, and what I'm doing, what my research topic is on that. So that's not part of the exam. And that'll be on Friday morning. It might start on Thursday evening. Okay. So yesterday you had Bobby. Thank you very much, Bobby, for taking care of an introduction to spectroscopy of hydrogen. And today I'm going to give a general introduction to the topic of astronomical spectroscopy and atomic spectra. And I wrote a book on this. When I came to doing the notes for this, I discovered that a student, I have to say of Indian origin, had managed to talk me out of my last copy of my own book last week. So I brought with me the book and the banner, which is the second edition. But this is actually the third edition. And the difference when we come to do line broadening, which is one of the topics we will cover, the third edition has line broadening and the second edition doesn't. But it's basically a book of a course I used to give at UCL, and that course was 32 lectures. You may have noticed you're not getting 32 lectures. So some of this will be a bit quicker, and there'll be some topics that are just missed altogether. So I'm going to talk about 2 subjects, spectroscopy and exoplanets, where you can date almost precisely when they started. And that's quite unusual in scientific subjects. Scientific subjects normally grow. This spectrum was taken by Fraunhofer in August 1814. And what he did was to make on a sunny day, he took his shutter and took a slit in the window, and then he projected the beam of light he got from the sun through a prism. That was something Newton had done. Newton had already made a rainbow from a beam of light, but Fraunhofer, who'd actually been as a young boy apprenticed to a glassmaker, was much better at making prisms than the one Newton had, and his prism was high enough resolution that he saw all these lines in the spectrums, what he called lines upon countless thousands of black lines. He had no idea what they were, but he was a very good scientist, and a few days later at night he repeated the same experiment using Betelgeuse, which is a nearby red giant star, so it's distinctly a different color from the sun. And what he realized was he got lines, but there were different lines. They were in different places. And he correctly concluded that somehow he was seeing the composition of the star he was looking at. He didn't know how, he didn't know why, but he realized that's what his tool was doing. And it took about 50 years before the first clue of what was going on came along. And this is an experiment certainly every school child in the UK does, and I suspect you have all done it, which is burning metals in a Bunsen burner. So Bunsen and Kirchhoff, actually, Bunsen invented the Bunsen burner to give him a nice stable source of heat so that they could burn sodium, potassium, magnesium, all different metals, get different colors. And what they realized was that they got lines in emission which matched exactly the absorption lines in the Fraunhofer spectrum. And indeed, I always used to talk about the D line. They only saw one. We'll come to why there are 2 of them later in the course, in fact, later today. And street lamps in the UK used to be orange because they had sodium. So you would see the Fraunhofer sodium lines on the street. Not anymore. We have LEDs these days, so sodium street lights are gone. So if you take a modern version of the same spectrum, this was taken with something called the UCL Echelle spectroscoph, which is called either Uckles or useless, depending on how you wanted to pronounce it. and it's just a long strip, very long strip. You can see the black Fraunhofer lines. Some of these are to do with the Earth's atmosphere, so-called telluric lines, and we'll talk quite a lot about the problems of doing spectroscopy through the Earth's atmosphere. And other ones are indeed due to the sun, and many of you may know helium was originally discovered from the lines it gave out in the sun before it was isolated by Ramsey at UCL 120 years ago. Right, so that's a little bit of historical background. So Bunsen and Kirchhoff, when they did this experiment, realized that there was some innate property of the atoms that they were looking at which allowed them to emit and absorb radiation at particular wavelengths, particular colors. They didn't understand why, and it took another 50 years and the discovery of quantum mechanics, and at the moment we're all celebrating 100 years since Heisenberg wrote his famous paper on matrix mechanics. And what quantum mechanics shows is that the energy levels inside the atoms are quantized, that is, they're discrete. So when you go up between two energy levels and you come down again, you do it with exactly the same wavelength light. So you have absorption spectroscopy, which goes up, and you have emission spectroscopy that goes down. And obviously, to get emission, you have to have the upper levels populated. To get absorption, you need a source of light to stimulate the absorption. And these satisfy something called the Ritz combination principle. Ritz realized that actually the structure of atoms and indeed molecules are this energy levels, and they're fixed, so that you can actually go round in circles, say here, here, and down here, and they add up in a particular fashion to give you combinations. And I'll come back to that. That's something I use right on Friday, because that's something I use very strongly in my current research project in a process we call Marple, and I'll talk about that on Friday. So in addition to the fact you can move between these energy levels, you also get things called selection rules. So you can't go from any energy level to any energy level. It's given by the rules of quantum mechanics, and a lot of what we're going to spend our time on over the next week is studying these. So the most common selection rule is that J, the finite angular momentum quantum number, varies by 1. It can also vary by -1 and 0, but basically it's capped. So you don't get delta J 2, 3, 4 transitions with usual dipole selection rules. You can get them under other circumstances, and we'll talk about at least one example of that as well. But you get these things called selection rules. So not all transitions are equally likely. Some don't happen at all. Some are very weak, but can happen with strange selection rules. Another important thing this thing captures is temperature. So whereas we think of as temperature as a macroscopic property, in fact, it's captured by so the temperature in this room is captured by the molecules moving around, and actually the temperature is simply an effect of the velocity of those molecules, but also the internal distribution in terms of energy levels within the molecule. And we will deal with this formula in more detail, but what these spectra give you is a handle directly on the temperature of the species you're looking at, providing there is a temperature, and I'll talk about that as well. I think I'll leave this till Friday. That's actually just how you store the results here. So to give a bit of background, I'm a physicist or a lapsed chemist, but not an astronomer. So I like to think in terms of energies or frequencies, because energy levels are very easily given in terms of energies. The Ritz principle is very simple in terms of energies, because you simply add and subtract the energies. Astronomers use telescopes. Telescopes work in wavelength, so the astronomers by and large think in wavelengths. So I'm afraid you're going to get a bit of a flavour of both. And just to make life a little bit more complicated, not all astronomers think in wavelengths. So the people who use very high energy, so X-ray, extreme ultraviolet, etc., they tend to use electron volts, which is an energy unit. And people at very short wavelengths, very long wavelengths, low frequency, tend to use hertz, in other words, frequencies, or even more bizarrely, kilometers per second, which is a Doppler shift. It's not a because what they do is they say the laboratory line here is here, and I'm observing something Doppler shifted that much from the laboratory line. It's a very odd methodology, particularly if you have a second line here, which then turns out to be given as a Doppler shift relative to the first line, which doesn't really make sense at all. But we'll see. I'm not going to do X-ray spectroscopy. It's in my book, but I'm not going to do it in this course. But we'll see examples of the long wavelength spectroscopy and the Doppler shifts. So I will talk largely in energy units. I tend to work in these rather strange centimeters to -1 units because they come up with convenient numbers. But frequencies in hertz are useful. EV can be useful for high energy transitions. So you can look at the electromagnetic, so it's useful to have a few conversion factors. 1 centimeters -1 is 30 gigahertz. So you can see that's a very large number of hertz. 3 times 10 to the 10 hertz is 1 centimeters -1. It's also quite close to 1 Kelvin. Now, I've put this up here with a little bit of trepidation because a Kelvin is not a unit of energy, though the astronomers quite often use it as a unit of energy. A Kelvin is a distribution. So if you have a gas at 1 Kelvin, it doesn't mean everything is exactly at 1 Kelvin. You have some Boltzmann distribution. You'll have some molecules that are effectively at 2 Kelvin and some which are much less than 1 Kelvin. And you can make mistakes if you say it's simply 1 Kelvin because you ignore the fact that you get a tail at higher energy. But anyway, the astronomers quite often use Kelvin as a unit of energy, and that's what they mean. I don't think it's good practice, and I will try not to do it. So you have a whole range, whole electromagnetic spectrum, and I've just done them out here for you in different energy units. So going right the way from the radio, very long wavelengths. There's a new telescope just opening, split between South Africa and Australia, called the Square Kilometre Array. And it does what it says on the tin. It's an array of telescopes covering at least the one in Australia, a square kilometre. It's going to be very long wavelengths. So we're going to get right down to these kilohertz frequencies and maybe even below with this. You'll see bending motions of very large molecules and rotational motions of very large molecules in principle. And they're going right the way up to gamma rays. There's not much atomic and molecular spectroscopy in gamma rays. It's more nuclear physics, but there are gamma ray observatories out there. In fact, there's a rather interesting side story about the discovery of gamma ray astronomy that the Americans proposed in the early 1970s to put up the first space telescope which would observe gamma rays. And they had a meeting to discuss it. And the scientists from the US Navy came along. And it turned out they had nearly 10 years worth of data on gamma rays because they'd been using gamma ray telescopes to look at nuclear tests being undertaken on Earth, particularly by the Soviet Union, which of course also give off gamma rays. And if anyone knows anything about gamma ray astronomy, it comes in bursts. And because the gamma ray will penetrate your detector in all directions, you get them anyway. I do wonder whether the first time a gamma ray burst was observed from astronomy, whether someone's finger didn't hover over the nuclear button, thinking that someone was exploding nuclear bombs somewhere. So it turned out the American military had actually been observing gamma rays for a decade and not telling anyone until the astronomers threatened to put up a telescope. But we're not going to talk about that. I'm not going to talk about X-rays, but I will talk about microwave, infrared, and visible ultraviolet astronomy. Okay? An important number that astronomers use, which basically gives the quality of their observation, is the resolving power. And I'll show you spectra which go from, I think, absolutely terrible resolution 8 to most good quality laboratory ones are tens of millions, if not billions. James Webb Telescope, to give you an example, as a current thing, claims to be high resolution. It isn't. It has a resolving power in best circumstances of 3,000. It's much better than anything has flown before, looking particularly at extrasolar planets, but it isn't high resolution. From Earth, you could certainly, a lot of Earth-based telescopes, you could do the sun at millions. The other Earth-based telescopes they're building at the moment are doing 100,000, 150,000. There's a whole range of different resolving powers. And when you're trying to compare with that, you need to understand what the resolution of the data you're looking at, because it makes a big difference for how you do your comparisons. So I will refer to R periodically and randomly through the talk as resolving power, and it's wavelength divided by the uncertainty in the wavelength. It gives you an idea of so the bigger the number, the better it is. So I think it's important to understand what we learn by doing astronomical spectroscopy. The short answer is nearly everything we know about the universe about us. So we can do positional astronomy with just photometry with white light. But if you want to know more than that, you want to know anything about composition or other things, you need to do spectroscopy. So if you observe a spectral line, what does that tell you? That tells you that that species is in the object you're looking at. So you learn immediately something about the composition. Normally, just knowing it's there is not really enough. You want to know how much. So, okay, we'll come to that. Second is, if you can understand which transition is, you can make a comparison of ground state and excited state, either absorption or emission, and that gives you a temperature. And we'll give I'll show you examples of that, of how you extract a temperature using spectra. If you can measure how strong the line is, you don't just get the fact that the species there, you get the abundance of the species, which is there, and that's important. So I spend a lot of my time working on just laboratory spectroscopy type things, and people are much worse at getting intensities than they are at getting line positions. They put huge efforts into getting line positions, and particularly long-wave spectra in the microwave, people don't tend to get intensities at all. And actually for the astronomy, that's useless. You need to know the intensity to get your, what's quite often called the column, because you have a telescope going out with, if you can think of it as a beam, looking across the universe, and you see all the objects in that beam, so it's sometimes called a column that you're looking at. Though if you're looking at a star, it has a point source, you know actually what you're looking at, even though by construction you have to be looking at everything in the middle as well, because you can't pick and choose where you look, you just look in a direction. I'll talk quite a lot on Friday actually about Doppler shifts, because it's become quite important in exoplanet spectroscopy. In general, Doppler shifts, just to do with the motions of the objects you're looking at, can give you a lot of information, and we'll see some of those also in the interstellar medium, showing you can resolve, for instance, the fact when you are looking along a beam, you may have several clouds in your line of sight, because they may have subtly different Doppler shifts, so that lines appear slightly different from each other from the different lines. But you also get information, you get things like, if you have something flowing out in both directions, you get a characteristic Doppler shift if you look across the flow with things moving that way and things moving that way, and you get a particular shape out of your lines as a result of it. So you can make deductions based on the Doppler shift, and then you can get the bulk motion, and people are probably aware that Hubble realized that everything was moving away from us, and therefore was able to extrapolate back to the Big Bang, and that all came from Doppler shifts of atomic lines. Otherwise, we wouldn't know that the universe started 13.5 billion years ago with a Big Bang. It just comes from extrapolating backwards on atomic lines. If you have really high resolution, you can get a line profile, you can get the shape of the line, and that contains information on the temperature. So a Doppler shift is a uniform shift. Doppler broadening is caused by the fact that the molecules are moving around due to temperature, so you get a broadening. So they're two slightly different mechanisms, both to do with the Doppler effect. So the physical conditions, such as the temperature and the pressure. Pressure is caused by collisions. That doesn't tend to happen in interstellar space. It's very diffuse, but in stars and in planets, where the atmosphere is denser, you can get collisions which give you information on the pressure. And finally, and I think it's going to drop off the end of the stream, not quite, just got it. You can also get magnetic effects. Now that's again something that's dealt with in my book, but I'm not going to talk about in this course because I can't do everything. But the magnetic field splits certain lines very strongly, other lines only very weakly. So for instance, it's well known in the sun that the sun has very strong internal magnetic field because of the splitting of particularly calcium lines, but things like sodium and other lines as well. they split them according to the magnetic field. You can see the different components. And that allows people to know that, for instance, sunspots are regions of huge magnetic activity, and that's what causes sunspots by looking at the magnetic field. We know rather less about the magnetic field everywhere else. Rather interestingly, you may be aware the Voyager mission left the solar system about 18 months ago, I think, and is now beginning to explore the magnetic field outside the solar heliosphere. So we're beginning to actually get the first in situ measurement of magnetic fields elsewhere. So I talked about being able to get abundances by looking at the total intensity, but there's a very important caveat on that, and that's something called optical thickness. So basically, if you have a beam of light, if you have enough of the compound that you're trying to absorb the light with, eventually you'll absorb all the light. And then it's not sensitive to how much more of that compound you have. It's optically thick. You basically absorbed everything. And when you're optically thick, you don't know what the column is. You just know that you've got enough there to absorb all the light. But it could be twice as much, it could be 3 times as much, it could be 10 times as much. You don't know. So you can't get an abundance from an optically thick line. So an optically thick line is thick if it absorbs the majority, basically all the photons going. You can't get abundances this way, and actually the line profile becomes very important for determining the absorption. And there's a rather interesting example on Earth, which is carbon dioxide, and we're all very worried about the amount of carbon dioxide in our atmosphere. But the main absorbing greenhouse gas lines of carbon dioxide, which are in the far infrared of CO2, are optically thick. That means that actually as you add more CO2, the amount of absorption does not go up linearly, it goes up as a logarithm. And that's because the line shapes are exponential, and it comes out from the broadening as the effect of line broadening, not the center of the line. Methane, conversely, which is also a serious greenhouse gas, but much, much less abundant in the Earth's atmosphere, if you add more methane, the effect due to methane goes up linearly because it's optically thin. And therefore you absorb at the middle of the methane lines. For carbon dioxide, you only absorb at the extra absorption of the line wings. So that's a terrestrial example. An important point astronomically is that it's not always possible to tell whether something's optically thick or not. And again, it's to do with this column. You don't know where your absorptions are relative to light. So you can be optically thick, but still get stuff this side of the thing you're looking at. And sometimes, so actually there are special tests. And again, they're dealt with in my book. I don't think I'm going to get a chance to talk to them about them this week, where you can compare different lines. You know the ratio of these lines should be. That'll tell you if they're optically thick or not. Actually, we will talk about it briefly, thinking about it. Temperature. Temperature only exists if you're in thermodynamic equilibrium. If you're not in thermodynamic equilibrium, temperature is not a useful concept. Though people sometimes do things like use partial temperatures in molecules. They say you have a vibrational temperature or rotational temperature, for instance, is quite a common approximation. But basically, if you're in thermodynamic equilibrium, you have a temperature. If you're not, you don't. And it's quite important to know which you are in. And there's something in astronomy called the critical density, which tells you whether a temperature is valid. So it's normally denoted sigma. Unfortunately, an awful lot of other things are denoted sigma, but this is denoted sigma. And it's the ratio, the rate of radiative decay, so the probability of emitting a photon compared to the rate of collisional excitation. And when it's, that should say above 1. So the critical value is 1. If you're less than 1, you need a full collisional radiative model. If you're more than 1, you could use temperature, you could use Boltzmann statistics. Life is much easier. Think about it. When you do a temperature, you just assume you have a distribution. If you do a collisional radiative model, you need to consider every single possible collision that a species can undergo. It needs a huge amount more information. But the interstellar medium is like this, and there's a mini industry amongst people who do chemical physics vaguely similar to me, looking at collisions with electrons, with hydrogen, with with hydrogen molecule and so on, so that people can establish these thermalization rates in the interstellar medium. So if you're an astronomer and you can't afford your own personal spacecraft, you have to look from the ground, and then you're always battling the atmosphere. This is an extremely simplified picture of the Earth's absorption, but what it's telling you is forget about doing any observing in the UV invisible from the ground. It's completely blocked out by absorption by the Earth's atmosphere. UV and X-ray, sorry. The visible, as we all know, is a nice window. That's why it's called the visible. So that's a good region. And the infrared is good in parts. Actually, it's less good than that picture implies. It implies that there are really solid windows. In fact, even the windows are a bit noisy. I've been observing, the only thing I've ever been observing is infrared observing, and you're battling strange effects of the atmosphere. And then again, the radio is a nice big window, so radio astronomy is quite easy. In fact, radio astronomy you can do from the UK as good as anywhere else on Earth. For infrared astronomy, you need to be high, dry, and near the equator. So I know India has a nice telescope up the Himalayas. It's high and dry. It's not as near the equator as it could be, but it's a good site. The best site in the world is in Chile, Atacama Desert, which is extremely dry, extremely high, and bang on the equator. And that's a real world-class center. But there are other ones. The one I've been observing on actually is Mauna Kea in Hawaii, which is also high, not that dry. Hilo is one of the wettest places on Earth, which is a local town. But it's very strange because when you're up there, you have a temperature inversion, and the clouds are a mile below your feet, literally. And it's raining like anything in Hilo, and you're looking at the stars. So it's quite an interesting sight. But anyway, so that's what you're battling. So you have to just worry about where you're observing, whether you can see it from the ground. You can always, in principle, go to space, but going to space is incredibly expensive, tends to lower your resolution, and you're fighting the whole rest of the known universe for time on that telescope, because there's only one telescope available and everyone wants to look at things, so that it's not an ideal solution, whereas most scientifically advanced countries have some sort of observing capability, so you can do ground-based observations. So I'm going to spend this morning talking about atomic spectra, carrying on from where Bobby spoke about yesterday. And with one exception, which I'll deal with here and again a bit later on, atomic spectra involve movements of electrons. The one exception is a 121 centimeter line, which is called the most important line in astronomy. I suspect all of you have mobile phones. Anyone got any idea what that has to do with the 21 centimeter line? What wavelengths do they broadcast your signals at? Any idea? X-ray, ultraviolet, infrared, radio? Radio. They go very long wavelengths, potentially 21 centimeters. So there's supposedly an agreement with the people doing antennae for etc. for mobile phones that they will leave certain lines untouched, of which the 21 centimeter line is considered the most important. It's not always agreed to by telephone operators. So actually modern day activity by man is becoming quite an inhibitor in these astronomical observations, because particularly at long wavelengths with modern communications are interfering with the observations. Also light pollution. I mean, Herschel discovered a planet from his back garden in the city of Bath in Britain. Bath is now a blaze of street lights and other lights. You would never do any modern astronomy, world-leading astronomy for your back garden in Bath anymore. It's far too bright. So there are particular dark areas, of which I'm sure the Himalayas is a marvellous one, but there are also designated dark areas around the world to try and combat that. So the strongest atomic lines are in the ultraviolet and the visible. The visible is good for astronomy. At the moment, there's very little good ultraviolet capability up. The Hubble Space Telescope is not particularly high resolution. Discrete lines or groups of lines, and they're prominent particularly in stellar spectra. I normally, and I should have put it up, have a great quote from logical positive philosopher Auguste Comte, who, when in the middle of the 19th century, people discovered how far the stars were away from us, and people were very shocked because they didn't really, you now know that the nearest one is 4 light years from us, and most of them are way, way further than that. But people didn't know that till they did triangulation measurements, getting the distance to the stars, using what they needed to know was what's called the astronomical unit, the distance of the Earth to the Sun. And then you do a measurement 6 months apart, you can triangulate. And they realized that the stars are hugely distant. And this was a really big cultural impact because people had not understood this. And Comte commented, "We will never know the chemical composition of the stars." What he thought was, we'll never go there, which may be true. But of course, spectroscopy means we actually know more about the composition of stars, even in other galaxies, than we do the center of the Earth, where we can't do spectroscopy. So, prominent features in most stars. And you should have already learnt about this yesterday, that particularly prominent in most stars are the hydrogen spectral sequences, which have names after the founders and are based on what the lowest level in each case. So Lyman goes to the ground state, Balmer to the n=2 state, and so forth. And you get a picture looking like that of the different series. And they're labeled alpha, beta, gamma, etc., going upwards, depending on how many ends you jump. And we'll come back to that because I'll show you helium plus is the same. So a stellar spectrum can often look like this. This is a quite simple one. I guess it's quite a hot star. So basically you've got, these are Balmer lines here. Starting where I looked at this yesterday, Balmer alpha is here, beta, gamma, delta, epsilon, and then at some point someone's Greek alphabet, certainly my Greek alphabet, gives up, and they become 8 and 9 and so forth. They just number them. There are more lines than there are left in the alphabet, so you have to number them at some point. In here, there's also a helium line, somewhere here we are. That's a helium. Helium 1 means neutral helium line there. And then there are two telluric lines. Telluric lines means Earth atmosphere, so those are oxygen lines from the Earth's atmosphere which are interfering with your spectrum. Right, fine structure. I don't think you did this yesterday, did you? You did? Okay, right, you've done this. So fine structure, every level in hydrogen, bar the S levels, bar the ground state in the other S levels, actually is 2 levels, because you can couple the angular momentum of the electron, the angular momentum of the orbit, and so that you get half and 3 halves, 3 halves, 5 halves, L plus half and L minus half in each case. So that gives you 2 lines. So fine structure splitting in hydrogen is very small. If you, like me, you do this as a theorist, and you use non-relativistic quantum mechanics, you don't get this. This is an effect from relativity. It took Dirac to derive a new version of quantum mechanics, which incorporated relativistic effects, to realize that you got this spin effect, and this whole fine structure splitting comes from relativity. Most people, like me, just add it on afterwards as a small ad hoc extra addition. So your general selection rules that n can change by any number and L changes by plus or minus 1, then have an extra selection rule based on the fine structure, which says that the J, which is the thing you get from the fine structure, could change by plus and minus 1 or 0. And I didn't put it there, but it can't go 0 to 0. So go 1 to 1, 2 to 2, or half to half, 3.5 to 3.5, but you can't go 0 to 0. So if you look at this little group here, these are all delta L plus or minus 1. That's delta J as 1. That's delta J 0. That's delta J 1. But that is delta J 2. So that one's not allowed. So that brings us to vector addition of angular momentum. And I want a bit of audience response here, or we're going to spend a very long time. So if you add 1 and 1 and they're just integers, what's the answer? Come on. Oh, I must well go home then. You can't add 1 and 1 and tell me the answer. 2, thank you. What's the answer at the back row? 1 add 1, what's the answer? 2.
And again, never kid. Right, I feed all audience and ask the question after long yet. All right? Otherwise, get me very hateful, very outdated this. You know it. Okay. So you've got 2 vectors. Papa, you did that. That. Good. So classically, if you have 2 vectors together,
Length 1, what are the possible results of the final vector? Can be 0. What else could it be? Anywhere between 0 and 2, exactly. So if you have a vector pointing here and a vector pointing here with some angle, you can go from this to this, and you take any value between 0 and 2. Okay. Quantum mechanically, when you add 2 vectors like this together, 2 angular momentum vectors, it's not like that. Now, I don't know whether you've done this, but I suspect some of you have. You can only get the integer gaps. So 1 plus 1 doesn't give you any value between 0 and 2. It gives you 0, 1, and 2. And the same thing works with half integers. So what would I get if I add those 2 together? What's the smallest value? Smallest value is 1 minus the other, so it's 1. 2 and 1 or 2's. So you get 1 and 2. So actually, in this picture here, what we've done is vector addition, so 3 plus a half and 3 minus a half gives you 5 and a half and 7 and a half. And we're going to use this quite a lot, so you need to know it, because there's basically a lot of spectroscopy is about adding up all the different angular momenta in the system. We've got 2, therefore, in the simplest system hydrogen. We've still got 1 more to introduce in terms of the nuclear spin. So even in the simplest 1 electron problem of hydrogen, we have 3 angular momenta to add together. So it's quite an important part of it. So I'm told I have to do that. Is that all? Yep, good. Fine. So, getting straight onto that. Hyperfine structure, as you can gather by the name, smaller than fine structure. And that comes from the nuclear spin. And the spin for the hydrogen atom is a half. So you have 1 more source of angular momentum. And you take J, this quantum number here, the fine structure, plus I, the hyperfine structure, and you add them together. So for the ground state, J is a half. You add another half to it, and the only answers you can get are 0 or 1. So you get 2 hyperfine levels for the ground state. And the 21 centimeter line gives you the transition between these 2 nuclear hyperfine structures. Okay? It's an incredibly weak transition. So ideal in things called Einstein A coefficients, the inverse of the Einstein A coefficient, 1 upon A, is the half-life. So it's equivalent to the half-life of a radioactive material, but now this is the radiative half-life. The half-life of the 21 centimeters line is approximately the lifetime of the universe. It's incredibly weak. That has significant advantages for the astronomers because it's always optically thin. You're never going to get enough hydrogen atoms in any column that it's going to be optically thick. So they can just assume it's optically thick. And as I think you all know, the universe is 90% made up of hydrogen. So this is how you monitor matter in the universe. You look at the 21 centimeter line, it tells you how much hydrogen there is in any direction you care to look at. So this is a very important line, I've already said several times. So I'm going to move on to atomic spectra. This is a very busy slide. I am going to go it several times. You should try and know this first column. The other columns are less important, but this first column is actually very important. And I will go through it. I'll do an exercise this evening on using it. Try and get you familiar with it. So these are the selection rules obeyed by general atoms. The hydrogen ones we looked at are a special case of these. So for instance, in hydrogen, you don't need to worry about the change in the spin because they're always spin half because there's only one electron. So some of these selection rules in hydrogen aren't needed. So the first thing to say, I've got three columns here: electric dipole, electric quadrupole, and magnetic lines. The electric dipoles are much stronger. I say 10 to the 6, but I think it's more like 10 to the 8, actually, times stronger. So that basically, if you have a dipole transition, it will happen. And you forget about the other ones. The quadrupole and the magnetic transitions are only important if you can't undergo a dipole transition. Now, there are quite a few cases where that's true, so we will talk about some of them. But if it can undergo a dipole transition, it will undergo a dipole transition, so those are the most important. Magnetic dipole transitions tend to be a bit stronger than quadrupoles, but they're roughly competitive with each other. We've already said that the universe is composed of hydrogen. A significant amount of that is hydrogen molecule, H2. And H2 does not have a permanent dipole. So actually, quadrupole transitions are important in H2. We'll discuss those. So these quadrupole selection rules will come back. And the other case, which is discussed quite a lot in the book, but I'm not going to talk about it today, is open shell atoms in their ground state. So you get something like the oxygen atom, and we will do that as an example, carbon atom this evening. Where you get more than one term arriving from the single configuration. And transitions within a single configuration are all dipole forbidden. And I'll come on to why that is. So then magnetic transitions become very important because they're the only possible transitions. And actually you can get the pressure of the interstellar medium by looking at these magnetic transitions. So, don't know what I've got back there. Yeah, so I wanted to go through, that's right, I'm going to go through all the symbols in this column, just explaining what they are. First thing to say is, you will notice that when we talk about hydrogen, we had lowercase letters, and now we've got uppercase letters. That's the important convention. If you have one electron, it's a lowercase. If you have many electrons, it's an uppercase. So when you, for instance, deal with helium, you may have two electrons which will have S1 and S2 for their two spins. They're lowercase s. When you add them together to give the total spin, that's uppercase S. And we will do that. So these are all uppercase selection rules except for the one electron ones here. And that's why these are lowercase. So the most simple, it's slightly cropped in my slide, don't mind. That should say sum over L, okay? No, I've lost it again, sorry. Anyway, the sum over L, you got that. So the parity is a single most important thing for determining whether you've got a dipole allowed transition. It's absolutely rigorous rule that if you have a dipole transition, the parity of the state, you have to do changes. And the parity actually is obtained by, if you have your atom, you bet all the coordinates through the origin. Now, there's a much simpler way of doing that, is that if you do things in radial coordinates and an angle, the radial coordinate is just a direction of value. It's not a vector, so it doesn't matter. And they just get the angular rule, and it depends on the sum of L, which I drew up there in a minute. So the parity is given by the sum of the L's of the electrons. And if it's an even number, it's even parity. If it's an odd number, it's an odd parity. And the Laporte rule says an electric dipole transition must change the parity. And I have a sideways note on that. Don't read anything about this on Wikipedia. It's garbage. It's interesting. I've been saying this I should change it really. Been saying this for 15 years, and all that's happened in 15 years is the garbage has grown longer. It's completely confused. It's don't. So bits of Wikipedia are great, but the one on the report rule is complete rubbish. Then the second sector we need to worry about is J. J is what you get. It's total angular momentum ignoring the nuclear spin. It's normally called the total angular momentum. When you add the nuclear spin, it's then called the final angular momentum, F. And it's a sum of L and S, where L is the total orbital angular momentum and S is the total spin angular momentum. You also use J for molecules, where it is also the total angular momentum ignoring nuclear spin, but you have other angular momenta in there, particularly the rotational motion, but you still use J. Mj is the projection of J on whatever axis you do, and by convention in atoms you take the z-axis, and basically Mj doesn't matter unless you have a magnetic field or an electric field. We're not going to talk about it, but if you have a magnetic field, you'll split all your levels according to the modulus of Mj, actually. L is the total orbital momentum, S is the total spin angular momentum. I'm going to give you some exercises later on in working out angular momenta for things. A very important rule is that if you have a closed shell, that is, you have all the orbits filled in a shell, 2p6, 3d5, 3v10 or whatever, 1s squared, all the angular momenta are 0. So for a closed shell, you can just ignore them. J equals S equals L equals 0. So when you're determining what the angular momentum of an atomic state is, you only need to worry about the unpaired electrons, the open shell electrons. Life can still get pretty tricky even with that big saving grace. But you remember this so you can waste a lot of time getting 0. J, and we've already dealt on this, could be integer or half integer. And that depends on whether the spin actually is integer or half integer. And actually, the atomic world divides into two, between bosons, named after a famous Indian, and fermions. Bosons have even J, fermions have odd J. Sorry, have half integer J. Let's start again. Bosons have integer J, fermions have half integer J. And they behave differently, as in Bose-Einstein condensates, which you can't form with fermions. And at the molecular level, you need to worry about something called orthopara, which I will try to do later on, seeing how we're doing for time, which give fundamental differences in how the molecules behave. And I was refereeing a paper this morning before breakfast, where they completely got this wrong. And their spectra were completely messed up. They had a load of lines that don't exist in their spectrum because they hadn't understood about the importance of actually using, in this case, bosonic statistics correctly. Okay, so we will come back to that by examples. So I think you already got this introduced to you briefly yesterday, but it's quite subtle, is spectroscopic notations for atoms. I'm afraid it's a property of spectroscopy. There's an awful lot of conventional notation in it. So we're giving quite detailed information in a very compact form. And if you're in the club, you know how to read it. And if you're not, it's very confusing. So you have 3 layers of atomic. You can label the atoms at. The top layer is a term where you don't consider the fine structure. And that's written as the spin degeneracy as a superscript times the orbit with a letter giving the orbital angular momentum. And I should have written this here, that S is 0, P is 1, D is 2, F is 3, G is 4, and so on. So this is the orbital angular momentum. My students insist on calling this 1s. It isn't. It's singlet S, because it's a degeneracy. This is not 3p, it's triplet p, because it's a degeneracy. 3p is an orbital. This is triplet p, is a term symbol. Rather confusingly, you can see that I put parity. I've got 0 superscripts on some of these, but by no means all of them, because the E for even is silent. I think this is a really unfortunate convention, because you never quite know whether someone's just forgotten to put the thing up there, or it's even parity. But it is the convention. Occasionally people put E's on there, but it's not normal. Normal is you leave it blank. So this means singlet S0 even. This is triplet P0 odd. Okay? And even to odd transitions are allowed. So it's this parity that gives you the Laporte rule. Without it, and that's why it's particularly important. So once you get the term symbol, then you can get the levels, and the levels are the fine structure resolved things where you put J in. So you go, I've just gone from here to here. Well, singlet S, that's S equals 0, that's L equals 0, so J has to be 0, so that's easy. Triplet P, that's S equals 1, L equals 1, so you get 3 things, 0, 1, and 2 for the 3 term values. Which way up they go is something we will come on to this evening in the problem class. Right, and then finally, which we're not going to talk about, there is something called states. And states are actually split by MJ. And you get states if actually you get degenerate states, but you get states if you have a magnetic field or indeed an electric field. Then also there's the hyperfine structure to do with the nuclear spin. And there's not really, that I'm aware of, a simple notation for that. I think you just state what F is after you've got the term value. So back to our electron transitions, and it says something important down the bottom, which has got left off. It says, if all of these rules are satisfied, you get what's called an allowed transition. Okay, that's probably fairly obvious. What is less obvious is that forbidden transitions are still allowed. So I tend to use the phrase strongly forbidden when they really don't happen. There doesn't seem to be an atomic physics word for it. But forbidden transitions still happen. So, sorry, this is a bit unfortunate. I've lost this. If you satisfy all the rules except the spin rule, you get something called an intercombination line. And if I was really clever, I'd do this in blue ink, but I don't know how to do that. So that's an intercombination line. So if you satisfy all the rules except the spin rule, you get an intercombination line. And that's because the weakest of those selection rules is S. The only good quantum numbers are J and parity, and the fine Lang momentum, whether it's J or F, depending on, I said J or parity. They're the only really rigorous rules. This is not a rigorous selection rule, and it turns out this is the weakest one. And relativistic effects will allow you to undergo transitions where S changes, but they are many orders of magnitude weaker than the strong ones. So they're called intercombination lines, and you get what are called forbidden transitions, and really lost a lot of this. So anything which, no, sorry, I didn't do this, did I? Right, that's better. So all those coloured boxes, they're forbidden transitions in the jargon. So anything which satisfies those selection rules. So in this case, fails one or more of these selection rules, but still satisfies this. That's a forbidden transition. Electric quadrupole is called a forbidden transition. A magnetic dipole is called a forbidden transition. Don't blame me, I didn't invent this terminology. I don't like it, but it's how everyone uses it. So if you read in an article, and you do regularly read, so-and-so line is a forbidden transition, this is what it means. Okay? So basically, they fail the dipole propensity rules, which are these ones for infrared transition, or the quadrupole, or the magnetic dipole. How am I doing for time, timekeeper? How much? All right, okay. So I'll probably do this, and that'd be a good place to stop, because then we get on to actual real atoms rather than general principles. So atomic spectra, you need to consider allowed versus forbidden. Basically, if it's allowed, it will happen in preference to forbidden ones. The forbidden ones are always many orders of magnitude weaker. So forbidden transitions in atoms are usually only important at long wavelengths, and that's because that's the point where you don't have allowed processes. That's not always true. In fact, I think the first forbidden transition I'm going to show you after we have a break will be in helium, and that's a very short wavelengths. So it's not, this is a generality, but it's not true. So the very important in the collision period is still a medium. You basically have an excited state of oxygen or carbon, and they only collide with something once every 2 months. So you have a long time to debate to give out your photon on a forbidden transition. They're unlikely to play a role in exoplanets, so that's a comment almost to me rather than any of you, because I work largely on exoplanet spectroscopy. Allowed transitions are always dominant, if possible. Prominent is stellar atmospheres. We've already seen that, and observed in exoplanets. Actually, I prepared this some time ago when the main thing, the original one that was observed was sodium, and I had a couple of examples of magnesium, but actually now there are lots of atoms observed in exoplanets, surprising number. And it's partly because it's easier to see the very outside of the atmosphere, which tends to be atomic in composition. So after the break, I'll get on to actual examples of spectra, but I think this is a convenient moment to stop. We've done the general principles. Any questions before we wrap up? Feel free to ping me an email, talk to me in tea break. If you have a question, I'm sure you're not the only person in the room who's wondering, why on earth did he say that? Yes, Robbie. Yep.
Repeat on the optical thick.
Yep.
And you said about the brilliance rushing the vertex will have an effect on that.
Yeah, so a ion is optically thick. It basically the photons are absorbed.
Okay.
So the simplest thing is if you have an absorption spectrum, you go right the way down so it hits them when that's clearly optically thick. If then you have revolution with it, you may be getting photons on the far side at what you're observing, and they're doing it astronomically. So you never quite know if it's optically thick or not. If it is optically thick, you cannot get the abundance. You could get there's already limits on the body photons that both photons without so you don't have intensity different. You don't have it. It's already said you can get them down, and then it's on the abundance, but it can be anything about that. So it's a real barrier to getting information is having not totally good spectrum. So how should I do it? Like for example, you said you see where it happens. So I'll give an example will come later in the week. Yeah, that's an Earth example. In astronomy, carbon monoxide is the second most common in the universe, particle in the universe. Hydrogen, unlike hydrogen, has a dipole, so if people monitor it to lots in the interstellar medium, the normalized of carbon is 16 oxygen, 12 carbon, 16 oxygen. That is quite often optically thick. So one thing they do there is monitor isotopically substituted, so maybe oxygen 18 or carbon 13, because they're optically thin. So that's one solution. But you have to be creative. You have to think of another line. You have to think of something else, a proxy. The more difficult and pressing problem is trying to work out when it's optically thin, and you can use fine structure components that I'll explain when we do fine structure. Any other questions? Yep. Right. Good question. Basically, and we go back. We have all these dipole searching rules. Shops thinking about a very strong transition, you have to obey them a lot. If you obey all of them except the spin one, so you go, for instance, from a triplet to a singlet, which is the example in helium we'll do in a minute, or after the break, then that is not strictly fully allowed, and it's called an intercombination line. And I'm sure there's some historic reason for that name, but I have no idea what it is. It's a strange name. And it's because the change in S is a less strong selection rule than the other selection rules. So these lines are stronger, they're intermediate in value,
between what I call later the forbidden transitions, these ones. So basically violating the delta L rule is a worse thing to do than violating the delta S rule. So intercombination lines are more likely than a delta L changing transition. And they're reasonably strong intercombination lines. If you're really desperate, if you just do hydrogen in a minute, and I suspect you didn't do this yesterday, 2s transition to 1s. You mentioned it yesterday.
So that's not allowed by every single rule. Yes, it's a problem that it ends off as a two-factor transition. Because it continues and at a very nice lifetime because of some type in the system.
So the forbidden is not actually forbidden.
So
The forbidden transitions are not actually
it always gets that something. In fact, it's a question how long it takes to get out. I'm actually feel with hydrogen 2s can also help because it mixes the 2s with the 2p and the 2p is allowed. So that's also another route the 2s can get out. Even a weak magnetic field will help it get out. So yeah, nothing stays in a high energy state forever. It always comes down somehow, but it's a matter of timescales. You're talking about nanoseconds against months to years to a lifetime of the universe in the 121 centimeter line. So it's all about timescales. So this, if you like, this intercombination line is not something I can prove mathematically. It's a ponderance. It's something you observe that the delta S is a weaker. The other selection rules you can show mathematically. You also show the approximations you make. The approximations effectively involve ignoring any relativistic effects. So that means actually when you get down the bottom of the periodic table, which you don't very much in astronomy, a lot of these rules become a lot weaker. And indeed, S becomes an almost useless quantum number when you're looking at molecules, atoms like uranium, or, as I've been worrying about recently, tungsten, which is important for fusion plasmas. So we're talking really at the top. So LS coupling is used, I will briefly mention JJ coupling at some point. LS coupling is used at the top half of the periodic table. The witching point on all this is iron. And you know where we're all going in atomic physics? We're all going to end up as iron, because iron is the most stable nucleus. So as the stars synthesize everything, iron is the bottom point where you get the most energy. It's also incredibly complicated because it's a midway between LS and J coupling. So you have to do it in lots of energy levels. I'll mention that very briefly in my talk on exoplanets. I've been borrowed. Okay, I think it's time for a cup of coffee.